Okay, good morning, everyone. Welcome back to the 5th Zoom consultation lesson for the June holidays. So today we'll be summarizing organic chemistry. So as mentioned just now, under organic chemistry, you have learned various homologous series. You have learned a number of reactions under each homologous series. You have also learned the conditions, meaning the temperature and the catalyst needed for each homologous series reactions, right? So you have learned a number of details, a number of things. So it is important to summarize it onto one page. So it is best that you can copy this summary down on paper, your notebook, or even better in your OneNote itself. So you can go to your personal folder under homework and start copying down the summary in OneNote. Okay, you have to ensure that you copy the summary down diligently to benefit maximally from it. Okay, now under organic chemistry, you have learned 4 homologous series, and that's where we will start today. You have learned alkanes, alkenes, alcohols, and also carboxylic acids. These are the 4 main homologous series you have been introduced to from the start. Okay? So we are going to start off by filling in some basic details of each of the homologous series. Namely, we are going to start filling in the general formula and the functional group. So the general formula for alkanes, CnH2n plus 2. Okay, so alkanes have the 2n plus 2. Now for alkenes, the general formula is CnH2n. So one quick way to tell whether something is alkane or alkene is to look at the ratio between carbon and hydrogen atoms. For alkenes, you will notice that the ratio of carbon to hydrogen is 1:2, meaning you should have double the number of hydrogen compared to carbon. That tells you it's an alkene. If it's more than double that of carbon, then it's not an alkene, it's an alkane. Okay, so I've given you examples so far. C2H6, 6 is more than double of 2, therefore it's an alkane. C2H4, 4 is double of 2, therefore it's an alkene, because it fits the general formula of alkenes, namely CnH2n. Then next we have alcohols, CnH2n plus 1 OH. Okay, finally, carboxylic acids, Cn minus 1, H2n minus 1, COOH. Now you notice that carboxylic acids have a -1 inside their general formula. The main reason why there's a -1 to the number of carbon is because there is already 1 carbon atom in the functional group. Okay, so let's not forget the COOH functional group already has 1 carbon atom. Okay, so that's a common mistake that most students will make. They will forget that there's 1 carbon atom in the functional group. Now, some of you may have looked at your textbook or you looked at notes from other sources, like other schools, for example. You will realize that there's a variation to the general formula of carboxylic acids. The variation given in your textbook is this. Okay, now this is a variation of the general formula. It is actually the same formula. The problem is, to use this, N is not the number of carbon. N is equal to the number of carbon minus 1. If you want to use the alternative general formula, which is found in the textbook, or if you want to use this formula, you must bear in mind, you need to -1 yourself. So at the end of the day, that's why I always teach the students the formula, which is in blue, which has Cn minus 1, H2n minus 1. That is much simpler, because all you need to do is you recognize that this carboxylic acid has 3 carbon, so N is equal to 3. So you just sub N equals to 3 into my formula. But this is just in case you read the textbook, you see a different general formula, you think, hey, did Mr. So teach wrongly? No, I didn't teach wrongly. It is because the formula in the textbook, you need to -1 yourself consciously, which some of you will forget. So I do not recommend the one in the textbook. I recommend the one that I've taught. That way you will not make a mistake. Okay? But you might want to take this down. Okay, moving on to the functional groups of each of the homologous series. So you have learned that the functional group is a group of atoms which gives the members of the homologous series its unique chemical properties, right? So every homologous series will have its own unique functional group, all right? So now we're going to move on to functional groups. So alkanes. Alkanes have no functional groups. What this means is that alkane, they do not have unique groups of atoms, which gives rise to a unique set of chemical properties. Okay? That means alkanes are the simplest organic compounds. They do not contain any unique groups of atoms. Now for alkenes, the functional group is the carbon-carbon double bond. All right? So this one I'm sure you know. Alkenes contain a carbon-carbon double bond. Alcohols contain the hydroxyl group, which is the OH group. Finally, carboxylic acids contain the carboxyl group, which is the C double bond O single bond OH group. Okay, so these are the functional groups of alkenes, alcohols, and carboxylic acid homologous series, respectively. All right. Okay, so we have finished the general formula and the functional groups of these homologous series. So now we're going to move on to a few more things before we go on to the reactions. So based on the functional groups, we are able to say whether something is a saturated hydrocarbon or unsaturated hydrocarbon. So alkanes are saturated hydrocarbons. So you need to know what the term means. Saturated means there is no carbon-carbon double bond. All right. Hydrocarbon means it is an organic compound made up of carbon and hydrogen atoms only. The word only is important. Only means it can only have carbon and hydrogen, these two elements. It should not have other elements like oxygen, chlorine, nitrogen. All right, it should only have carbon and hydrogen. So alkanes are saturated hydrocarbons because they are organic compounds made up of carbon and hydrogen atoms only, and they do not contain carbon-carbon double bonds. So that's for alkanes. Alkenes are unsaturated hydrocarbons. Okay, so you need to know this. All right. Alcohols and carboxylic acids are not hydrocarbons in the first place because alcohols and carboxylic acids have oxygen atoms inside them. So alcohols and carboxylic acids will not be considered hydrocarbons. Okay? So you can write down these are not hydrocarbons. All right? Now, next we move on to the reactions. So under the reactions, you have probably learned a few. The reactions of alkanes, combustion. Okay, so combustion, I won't go through in detail. You should already know combustion is the reaction where the hydrocarbon, the organic compound, burns in oxygen gas. So combustion, there are two types, complete, incomplete. complete combustion occurs when it's in excess oxygen. So complete combustion produces CO2 and H2O only. Okay? Whereas incomplete combustion produces carbon monoxide. Now, besides combustion, it also takes part, in substitution reactions. Namely, substitution with chlorine in the presence of UV light. Okay? So take, for example, you have methane plus Cl2, it forms CH3Cl plus HCl. And the condition needed is UV light. Okay, so this is a short summary of alkanes. Then we move on to alkenes. Alkenes undergo combustion as well. So alkenes can also burn in oxygen gas. If the oxygen is in excess, it undergoes complete combustion to produce CO2 and H2O. Now, besides combustion, alkenes undergo addition. And this is the one that is important. Because addition, there are basically a number of additions possible. The first one is hydrogenation, where you add hydrogen. Second one is bromination, where you add bromine. Third one is hydration, where you add steam. The last one is addition polymerisation, where it adds to itself. Okay, so there are 4 different types of addition, but they are all considered addition. Okay, now why are they considered addition? They are all addition reactions because they all result in the formation of a single product with no loss of atoms. So whenever you have an addition reaction, there's only one single product on the right-hand side. Okay? There's no 2 products, 3 products on the right-hand side. All right? So I'll give you an example reaction. So something simple like C2H4 plus Br2. The product form is just this. Okay? So there's only one thing on the right-hand side of the equation. This tells you that you only form one single product with no loss of atoms. Now, so if you look through all the prelim questions, you would have seen there are questions being set on something called atom economy. Atom economy basically expresses the MR of the desired product over the total MR of the products. Because there's only one single product in addition, the atom economy is 100%. Okay? By definition, addition reactions result in 100% atom economy. Because only one product is formed. This means that that product must be the useful product, the desired product that you want. There is no byproducts in an addition reaction. Okay? Can? Now, learning the addition reactions is important, but equally important is learning the conditions for the addition reaction to take place. And the conditions are not the same. For hydrogenation, what you need is you need a specific temperature and you need a specific catalyst. Hydrogenation's temperature is 200 degrees Celsius. The catalyst used is a nickel catalyst. Now, the nickel is usually given in the form of a powder. This is because powdered nickel has a larger surface area to volume ratio. Okay, so the catalyst in hydrogenation is nickel. Usually we use powdered nickel catalyst. Now for bromination, you just need bromine water at room temperature. This one doesn't require heating. Hydration requires steam, and the steam is delivered in a specific temperature, specific pressure. Okay, so what is the specific temperature and pressure for hydration needed? Okay, do you recall that for hydration? Okay, we need 300 degrees Celsius. So temperature. Pressure is 60 atmospheres. And you need phosphoric acid catalyst. Finally, for addition polymerization, you need high temperature and pressure, and also a catalyst. Now, we do not learn the catalysts for addition polymerization in O level. Okay, there are special catalysts for polymerization to take place. So I'm sure you have seen so far, the catalyst is not the same. Okay, nickel is the catalyst for hydrogenation. In fact, that is an important industrial use of nickel. Nickel is used as a catalyst for hydrogenation of alkenes. Okay, so different catalysts will catalyze different reactions. So far we have finished alkanes and alkenes. Now for alcohols, alcohols undergo combustion and also oxidation. Now there are two types of oxidation. Okay, namely with atmospheric oxygen or with acidified KMNO4. Okay, now in the lab, obviously we will use KMNO4 with acid because in the lab we have access to chemicals. We should use acidified KMNO4 to oxidize alcohols. But alcohols can also be oxidized if it's left open to the air because air contains oxygen. Oxygen is an oxidizing agent. It can oxidize the alcohols to the carboxylic acids. So importantly, when oxidation takes place, it forms a carboxylic acid. Okay. Now the final reaction of alcohols is actually esterification, which we just learned, okay, in the last chapter. So alcohols can react with carboxylic acids to form esters. Okay, so these are the three types of reactions that alcohols can undergo. Right? Finally, carboxylic acids. Now, carboxylic acids do not undergo a lot of reactions. Carboxylic acids mainly undergo acid reactions. So acid reactions can be with carbonate, metals, or bases. So this is where we wrote the equation for the reaction of a carboxylic acid with a carbonate, metal, or base. Okay, so I'll give you an example. Let's say you have ethanoic acid, CH3COOH, plus sodium carbonate. So acid plus carbonate forms a salt. You need to know how to write the salt. So if you recall, it was a bit strange because what happens is that, okay, we will need to this is the balance equation. Yeah, it's a bit strange sometimes because the sodium is actually put at the end of the formula of the salt. Okay, that's how organic chemistry usually would write this equation. Okay. And finally, one last reaction, okay, involving the carboxylic acids, of course, esterification. So as mentioned, esterification involves the reaction between an alcohol and carboxylic acid to form esters. Now, this is just a very, very quick summary. As you can see, I've written like everything out. This is a quick summary of the types of reaction which each homologous series will undergo. Okay. Okay, so now that we have gone through the general formula, functional group, all the different types of reactions that each homologous series can undergo, what's also important when summarizing is learning and questioning how do I convert from one homologous series to another homologous series. For example, how do I go from alkene to alkane? Right? Is there a reaction that allows me to convert an alkene to an alkane? So to understand and answer this, you need to know what types of reactions do alkenes undergo in the first place. Alkenes can undergo combustion, but combustion, complete combustion produces CO2 and H2O, doesn't produce an alkane. So what reaction from an alkene will produce an alkane? Well, the next type of reaction is addition. But we already know that addition has a number of different examples. So which example of addition will produce an alkane? Amongst the 4 examples that we learned just now, hydrogenation, bromination, hydration, and addition polymerization. The one that produces an alkane is hydrogenation. All right. Hydrogenation allows me to go from an alkene to an alkane, meaning I can go from ethene to ethane, from propene to propane, from hexene to hexane. And let's just recall what's the conditions needed. Firstly, we need to add H2. The conditions needed, 200 degrees, nickel catalysts. That's hydrogenation. Okay, so that's how we go from alkene to alkane. Now, that's the first conversion. The next conversion that we can begin to question is, how can I go from alkene to alcohol? If I start from an alkene, how do I go from an alkene to an alcohol? Is there a reaction? Of course there is. It's again one of those addition reactions of alkenes, right? Alkenes, there's hydrogenation. Hydrogenation produces alkane. Bromination produces the bromoalkane. Then we have hydration. If I were to add steam, I produce an alcohol. So steam is H2O gas. This takes place at 300 degrees Celsius, 60 atmospheres, H3PO4 catalyst. Okay, so that's how you go from alkene to an alcohol. So for example, if we started with ethene, ethene plus steam becomes ethanol. Propene plus steam becomes propanol, and so on, so forth. All right. The next thing we can question. So now that I have formed my alcohol from my alkene, how do I go from alcohol to carboxylic acids in the lab? Alcohols undergo some reactions: combustion, oxidation, esterification. Which reaction allows me to go from alcohol to carboxylic acid? That is oxidation. This is where I use acidified KMNO4. Okay, and we went through this under enrichment. You need something called reflux. So you have a reflux condenser set up, okay, so that you can cool and condense the alcohol back into the reaction flask. Okay, so in case you don't know what reflux is, you should revise chapter 23, enrichment. So these are the 3 conversions that immediately you should know how to do if you understood organic chem. And this is what I mean by understanding and applying. This is not in the textbook. But if you are able to summarize and write out these 3 conversions, this means you have understood organic chem. Okay? Okay, so we have seen 3 different types of conversions. All right, between alkenes and alcohols, alkenes and alkanes, and finally alcohols and carboxylic acids. All right, now, so we can add on to this understanding. In organic chemistry, you have also learned some other reactions. Take, for example, and let's use a different color for this. You are able to convert alkanes to alkenes. Specifically, you are able to convert large alkanes to smaller alkenes. So once I write down large alkanes to smaller alkenes, it's quite clear what reaction this is, right? This is obviously cracking. So cracking involves the conversion and breakdown of larger hydrocarbons to form small alkenes. So alkenes are obtained industrially through cracking of the hydrocarbon fractions after fractional distillation of crude oil. Okay, cracking of the hydrocarbons is how we obtain alkenes. Next, we go to alcohols. Alcohols are produced industrially for industrial use through hydration of alkenes. So we have already drawn there, right? Alkenes undergo hydration, become alcohol. That is how you make an alcohol on an industrial scale. That means the alcohol is used as a solvent, as a chemical to make other things. That's called industry. However, alcohols are also commonly found in beverages. Alcoholic beverages are not made by hydration. Alcoholic beverages, alcoholic drinks, are made through fermentation. So glucose solution can undergo fermentation. But when it undergoes fermentation, it produces only one type of alcohol, which is ethanol. That means you only form the 2-carbon alcohol. And what was fermentation's condition? 37 degrees Celsius, and you must have yeast, you must have absence of oxygen, or what we call anaerobic conditions. Now, the reason why we use a different color to represent cracking and fermentation will become apparent later. But let's ensure we use a different color, okay? So now you have added to your understanding, right? You have also learned cracking. Cracking is how we get smaller alkenes. Fermentation, you have also learned. Fermentation is a process by which glucose solution can be used to produce ethanol, the 2-carbon alcohol only. All right. So the main reason why we have used a different color to represent these reactions of cracking and fermentation, it is because if you notice in fermentation, you started with 6 carbon atoms in each glucose molecule. But it produced ethanol. Ethanol only has 2 carbon atoms per molecule. So we say that these are, the blue color represents step-down reactions. So the blue color represents a step-down reaction. A step-down reaction is where the number of carbon atoms per organic molecule decreases. So cracking is step-down because it decreases the number of carbon per molecule of organic compound. Similarly, fermentation is step-down Because at first glucose has 6 carbon atoms, then it produces ethanol, which has 2 carbon atoms. So per molecule of organic compound, there are fewer carbon atoms. Okay? So these two are step-down reactions. You decrease the number of carbon per molecule. Green color, the number of carbon remains the same. So in hydrogenation, hydration, oxidation, we do not change the number of carbon. All right? You do not change the number of carbon atoms. Meaning, if you started with ethene, 2 carbon, you reacted it with, say, steam, it produces ethanol, 2 carbon also. Now, why is this important? Do you realize we have said step down? We have said remain the same. You have not learned how to increase the number of carbon, right? And indeed, you have not learned how to increase the number of carbon. For example, you can't go from ethene to propanol. You have not learned how to do that. So ethene to propanol, you don't know how to do it. Okay? Similarly, you have not learned how do you go from ethanol to butanoic acid. You have not learned. Okay? So, if the question asks you, which cannot be achieved by a single reaction, which one have you not learned? Which one have you not learned how to achieve? How to increase the carbon? You have not learned how to increase the number of carbon atoms. All right. So this has appeared in MCQs before. They have given students 4 options. Students have to choose which option cannot be done. Then students are confused. Huh? How will I know which cannot be done? Yes, you know. Because you have learned that you can keep the number of carbon the same, you can step down through cracking or fermentation. But you have not learned how to increase the carbon. So you have not learned how to go from ethene to propanol. Nope. Okay? And indeed, from ethene to propanol, you can't achieve that in a single reaction. You need to go through a number of steps to get to propanol. Okay, which you have not learned. Okay? Now, the good news is once you have gotten to this stage, if you just zoom out, I will zoom out for you to see, you have basically summarized most of organic chem. All right, you have just left one part left to summarize, which is esterification, which we're going to do quickly now. Okay. Now, esterification, I will do it separately from the main summary, not because it's not linked, okay? Esterification is linked. It involves an alcohol plus a carboxylic acid, right? Now, this forms an ester. But many students forgot the next part, which is the water. Please don't forget that it forms water, okay, in addition to the ester. Okay, you cannot forget that. Now, you notice that Mr. So hasn't drawn the arrow. Depending on the textbook that you read, the arrow could be a single arrow, which is irreversible reaction. But typically, esterification tends to be reversible, especially if you had used a carboxylic acid. Okay? Now, the catalyst for this is concentrated sulfuric acid. You must use consulfuric acid. Dilute sulfuric acid wouldn't work. And it needs to be heated with reflux. So again, you see this word reflux. This is from chapter 23, enrichment, which we went through in class. You need the reflux condenser set up whenever you have alcohols reacting, because alcohols evaporate very easily. So if you don't have reflux, the alcohol will just evaporate totally and it wouldn't form any ester. Okay? Now, the difficulty that most students face is obviously, what if they needed to deduce the ester formed. For example, if you have propanol and methanoic acid, all right, what is the ester going to be called? Okay, so remember, the name starts with the alcohol. Propanol will form propal. The second part of the name comes from the acid. Methanoic becomes methanoate. So you must recognize the alcohol's name comes first, then the carboxylic acid's name. And let's not forget about water. Now, in terms of drawing the structure, propanol. So let's assume it's propan 1-ol. Propanol. Okay, we are going to use propan 1-ol as an example. I know there's another isomer, but we're not going to talk about the other isomer. Okay, so how do you draw the ester? Now, the ester linkage contains this. If you know it's an ester, draw the ester linkage first. This is from the acid. That means this portion on the left is the acid. Whereas this portion on the right, the O single bond, is from the alcohol. So the alcohol got how many carbons? You use propanol, so it's 3 carbons. 1, 2, 3. Ensure every carbon has 4 bonds around itself, and you are done. So this is the structure of propyl methanoate. Now, this is how I've drawn. Can you also draw like this? The answer, of course, is can. Always remember, the single bond O comes from the alcohol. So in this case, 1, 2, 3 carbon alcohol. Okay, the other side is from the carboxylic acid. So it's just 1H, right? Now these two are the same, identical. They are not isomers, they are identical. Okay, they are just different ways of drawing the same structure. They are not isomers of each other. Okay, so in the exam, you will see both versions, right? Used interchangeably. So the idea is not to memorize how the ester linkage looks like. You need to be able to dissect the ester linkage, divide it up. So you must recognize the C double bond O portion belongs to the acid. The O single bond portion belonged to the alcohol. That way, you will never get confused. Okay? So that is how we actually draw the structure and name an ester. So remember, the structure, you must be able to dissect the ester linkage. Okay? In terms of name, you must know that the name of an ester starts with the alcohol. The second part of the name then is the carboxylic acid. Okay, so now that we have gone through how to name and draw the structures of esters, okay, you must also know if I give you the structure of the ester, you must be able to reverse engineer and work backwards to get the starting alcohol and carboxylic acid. Now, before we move on to anything else, if you just look at the formula of the ester, okay, so just look at the formula of the ester and work out its molecular formula. You will realize the molecular formula has 4 carbons in total. Okay, the hydrogens, how many hydrogens does it have? 8. How many oxygens does it have? 2. So the molecular formula of propyl methanoate is C4H8O2. Now, if I ask you to draw butanoic acid, butanoic acid has 4 carbons. Remember, the functional group is COOH already. So if you just look at this now, butanoic acid is also C4H8O2. So this is propyl metanoate that we draw, the ester. Butanoic acid is also C4H8O2, meaning they have the same molecular formula, right? Their molecular formula of propyl methanoate and butanoic acid are the same, but they have different structural formula. Clearly, one has an ester linkage, COO. The other one is not ester, it's COOH, right? So that one is a carboxylic acid. So this tells you that propyl methanoate and butanoic acid, they are isomers. So in short, we can conclude ester carboxylic acid isomers of each other. If they have total, so propyl methanoate, 3 carbon, 1 carbon, so 4 carbon. So propyl methanoate is an isomer of butanoic acid because they both have 4 carbon atoms in total. Okay, so this is important to note. Many students didn't realize this until the question tested them on this. You need to know that esters and carboxylic acids can be isomers of each other, provided they have the same total number of carbon atoms. Okay, so that's the first important thing to note. So if you recall in class, I made you all calculate the MR, write the molecular formula, so slowly, right? We spent one lesson just doing this. We spent one lesson just calculating MR of carboxylic acids and esters. This is to show you that, hey, actually esters may have the same molecular formula as carboxylic acids if they have the same total number of carbon atoms. Therefore, they are isomers of each other. Okay? Now, beyond saying that esters and carboxylic acids are isomers of each other, there's another common thing that I would like you to know, which is what we ended off term 2 with. If you recall our last chemistry lesson in term 2, we went through chapter 23, enrichment, where I threw you a sort of a curveball situation, right? What was the curveball that I threw some of you if at the end of the lesson? Now, we know that alcohol plus carboxylic acid forms ester and water. Okay, and water, don't forget the water. But what if I have a molecule that has a carboxylic acid on one end? And what if it also had an alcohol on the other end? I mean, there are molecules like this, right? This is an equally valid structural formula. Every carbon atom has 4 bonds. So what is stopping an organic molecule from having 2 functional groups? 1 carboxylic acid, 1 hydroxyl alcohol functional group. It's perfectly possible. Agreed? So, given that the alcohol functional group, okay, we just call it hydroxyl is the proper word, hydroxyl group, and the carboxyl group, they are in the same molecule. So what can happen? There are 2 possibilities. The first possibility is, well, maybe they can react with other molecules of itself, right? For example, this carboxyl group can react with the alcohol group of another molecule. And so let's draw that. This carboxylic acid highlighted in yellow can react with the alcohol of the other molecule, right? And then this alcohol can also react with the carboxylic acid of another molecule, right? And so on and so forth. So what is this? This is polymerization. So the idea is polymerization can take place. Now, this polymerization is not the same as alkenes. Alkenes undergo addition. This is not addition. This is esterification. Esterification produces a small molecule like water in addition to esters. So this is condensation, polymerization. All right. So you can go on and on and on and on. Do you agree? So I'm sure you agree that it goes on and on and on and on. Therefore, we do not draw the structure on and on and on and on. We can't do that. It's too much work, right? It goes on forever, you know, for 1,000 times, 1,000,000 times. So what happens is 1,000,000 molecules of this same molecule can polymerize on and on and on. It's as if you are making a necklace and you are threading like thousands and millions of beads together. That is the same concept. You are basically making a very long polymer chain. So we cannot draw the very long polymer chain. We can only draw the repeating unit. And the repeating unit is this. Now this is the repeat unit. To draw the polymer or to represent the polymer, we put N, where N is a large number. It signifies how many times the thing has been polymerized. Okay? Now this is what we'll do when school reopens. Okay, this is condensation, polymerization. Okay, so this is repeated N times. That gives you the whole polymer. Now that is one possibility, right? But there's another possibility, you know. That means instead of itself reacting with other molecules of itself, can just one single molecule react within itself? Can the alcohol somehow curve and bend around and reach the carboxylic acids? I know it might sound very ridiculous to you. It looks like all the bonds are straight, but in reality, the bonds aren't linear like this, okay? The atoms and bonds have a bond angle and it's not linear like this, all right? So the alcohol group is able to react with the carboxyl group within the same molecule. Within the same molecule, this is called the intramolecular esterification. Okay, this occurs when the alcohol and the carboxylic acid functional group are both found within the same molecule. So the alcohol and the carboxylic acid can react together within the same molecule. Now, when you have intramolecular reactions, what it results is a cyclic compound formed. Okay, so now we are going to do a little bit of color coding so that you don't get lost. First, Mr. So shall draw what the compound looks like. Okay, so I've color coded a little bit. The blue color obviously is from the alcohol functional group. The yellow color was from the carboxyl functional group. So this is the structure. Of course, it also produces water. Don't forget, it produces water, okay? But this is the structure of the cyclic ester. So whenever you have intramolecular reactions, it results in the cyclic ester formed. Okay. So we have seen both possibilities, condensation, polymerization, and intramolecular esterification. Now, obviously, these are two different reactions. They result in two different products. One results in a condensation polymer. The other one results in a cyclic ester, which is not a polymer, right? So which type of conditions will favor each type of reaction? Well, if you think about it, for polymerization to take place, it needs to react with many molecules of itself. So this takes place when the concentration is higher. When you have more molecules in the same volume, obviously they will have a higher frequency of collisions. Therefore, the polymerization is favored. Because for polymerization to take place, it needs to collide with other molecules of itself. Whereas intramolecular is within the same molecule. Why would it react within the same molecule? When there are very few molecules of itself. When the concentration is low. So low concentrations will favor the intramolecular reaction. Okay? And that really brings us to the end of what you need to know from alkanes, alkenes, alcohols, carboxylic acids, and esters. So if you have been able to summarize all the information this way, you would have effectively summarized something like 3 chapters worth of material into just one OneNote document. Okay? Now, the ability to be able to summarize things this way reflects understanding. So don't just memorize. You need to question yourself, can you summarize things this way for electrolysis, for metals, for other chapters that you have learned previously? If the answer is yes, you are able to summarize things this way, then I think it will be helpful for you to summarize these things this way. And this is a useful skill you need to bring with you onto poly, onto JC. Because when you go on to poly and JC, you will have many topics to study, regardless of what course you are taking. And the key to studying well is always to be able to summarize your own notes this way. Okay? And that brings us to the end of today's lesson, the organic chemistry summary. Now, tomorrow's lesson, we will again summarize. But tomorrow, I would like to summarize separation and purification, which is a Sec 3 topic. Okay? So I shall see you at the same time tomorrow. Okay? Thank you.